Close your eyes and imagine our Sun, a sphere so immense that over 1 million Earths could fit inside it. It dominates our sky, lights our days, warms our world. Yet, in the cosmic hierarchy of stellar giants, our Sun is tiny, a modest dwarf compared to the true monsters that exist in deep space. Tonight, we'll journey to the largest star ever discovered, Stephenson 2-18, a hypergiant so colossal that if placed where the Sun sits, its surface would extend past Saturn's orbit, swallowing every inner planet and gas giant up to the ringed world itself. We'll explore what makes stars grow to such incomprehensible sizes, why some become hypergiants, while others like our Sun remain relatively small, and what physical limits prevent stars from growing infinitely large. We'll witness dramatic scale comparisons, stars thousands of times wider than the Sun, with volumes containing billions of solar systems. We'll understand the physics of stellar gigantism, from the tenuous outer envelopes to the dense cores burning exotic elements. And we'll confront the ultimate question: could even larger stars exist somewhere in the vast universe, hidden in distant galaxies beyond our ability to detect? This is the story of extremes, where nature pushes size to its absolute limits, creating objects so vast they challenge human imagination and comprehension. When we say a star is the largest, we're talking about physical size, how much space it occupies, how far its surface extends from its center. This is different from mass, which measures how much matter the star contains, or luminosity, which measures how much light it emits. The Sun has a radius of about 696,000 kilometers, roughly 432,000 miles. That's the distance from the Sun's center to its visible surface, the layer we see when we look at it. This surface isn't solid like Earth's ground. Stars are made entirely of gas, mostly hydrogen and helium, held together by gravity. The surface is simply where the gas becomes thin enough that light can escape into space. Measuring a star's size isn't straightforward. For nearby stars, astronomers can use interferometry, combining light from multiple telescopes to directly measure the star's apparent size in the sky. Knowing this apparent size and the star's distance, they can calculate its true physical diameter. For distant stars, the method is more indirect. Astronomers measure how bright the star appears and estimate its distance. This gives the star's true luminosity, how much total energy it radiates. They also determine the star's surface temperature by analyzing its color and spectrum. Hotter stars glow blue-white, cooler stars glow orange-red. Here's the key insight. A star's luminosity depends on both its temperature and its surface area. A small, very hot star can be as luminous as a large, cool star. By knowing luminosity and temperature, astronomers can work backward to figure out how large the star must be to produce that much light at that temperature. This method has uncertainties. Distance measurements can be wrong, affecting luminosity calculations. Temperature estimates have margins of error. For cool giant stars with extended, fuzzy atmospheres, defining exactly where the surface is becomes somewhat arbitrary. These uncertainties mean that published stellar sizes often have error bars of 20 or 30%. When we say a star is 2,000 times wider than the Sun, the true value might be anywhere from 1,600 to 2,400 solar radii. For the largest stars, even with these uncertainties, the sizes are staggering. Stars come in an enormous range of sizes. The smallest stars, red dwarfs, are about 10% the Sun's diameter. White dwarfs, the dense remnants of dead stars, are roughly Earth-sized despite containing half the Sun's mass. Neutron stars are even more extreme, about 20 kilometers across, but containing more mass than the Sun, compressed to incredible densities. At the other extreme are the giants and supergiants. Red giants are evolved stars that have swelled to 10 or 100 times the Sun's size. Red supergiants are even larger, hundreds of times wider than the Sunday. And at the absolute peak are the hypergiants, the rarest, largest stars in the universe. Hypergiants are stars in the final stages of their lives, having swollen to truly extraordinary sizes. They're unstable, pulsating, losing mass rapidly through powerful stellar winds. They represent such a brief phase in stellar evolution that only a handful exist in our galaxy at any given time. The largest known stars are all red hypergiants. Red indicates they're cool. Their surface temperatures are only around 3,000 to 4,000 Kelvin, compared to the Sun's 5,800 Kelvin, or hot blue stars exceeding 20,000 Kelvin. This coolness is crucial. For a star to grow truly enormous, it must be cool. Hot stars, even very luminous ones, cannot achieve the same gigantic radii. Why must the largest stars be cool? It comes down to how stars radiate energy. Every square meter of a star's surface radiates a certain amount of energy depending on its temperature. Hotter surfaces radiate far more energy per square meter than cooler surfaces. A blue star with a surface temperature of 20,000 Kelvin radiates about 40 times more energy per square meter than a red star at 4,000 Kelvin. If two stars have the same total luminosity but different temperatures, the cooler star must have much more surface area to compensate. It must be much larger. This is why the biggest stars are all cool red giants and hypergiants. Their low temperatures force them to balloon to enormous sizes to radiate their energy. The larger stars also tend to be very luminous, hundreds of thousands or even millions of times more luminous than the Sunday. Combining high luminosity with cool temperatures creates the recipe for maximum size. Volume grows even faster than radius. If a star is 10 times wider than the Sun, its volume is 1,000 times larger, 10 cubed. If it's 100 times wider, its volume is 1,000,000 times larger. The largest stars, roughly 2,000 times the Sun's radius, have volumes about 8 billion times the Sun's. You could fit 8 billion suns inside one of these hypergiants. Yet paradoxically, these enormous stars don't necessarily have enormous masses. Many red hypergiants started with only 15 to 30 times the Sun's mass, far less than their volume might suggest. By the time they've swollen to hypergiant size, they've lost significant mass through stellar winds. Their outer envelopes are incredibly tenuous, with densities far lower than Earth's atmosphere. This combination, huge size, relatively modest mass, very low density, makes hypergiants utterly unlike any object in our everyday experience. They're more like incredibly large, glowing clouds of gas than anything solid. With these concepts in mind, we can now identify the specific contender for the title of largest known star, and understand what makes it so extraordinary. The current record holder for the largest known star is Stephenson 2-18, a red hypergiant located approximately 19,000 light-years from Earth in the constellation Scutum. This star is so large that if it replaced our Sun, its surface would extend past the orbit of Saturn. Stephenson 2-18 resides in a massive open cluster called Stephenson 2, one of the largest clusters of its kind in our galaxy. The cluster contains numerous massive stars. including several red supergiants and other extreme objects. It's a stellar nursery on a grand scale, producing and destroying massive stars in rapid succession. The cluster's distance, 19,000 light-years, places it far beyond what we can see with the naked eye, deep in the Milky Way's disk. At this distance, the cluster appears faint despite containing many luminous stars. Interstellar dust also obscures the cluster, absorbing visible light and making observations challenging. Astronomers study it primarily using infrared light, which penetrates dust better than visible light. Stephenson 2-18's estimated radius is approximately 2,150 times that of the Sun, though estimates vary from about 2,000 to 2,500 solar radii, depending on the measurement method and assumptions used. Taking the middle estimate, the star has a radius of roughly 1.5 billion kilometers. To put this in perspective, Earth orbits the Sun at a distance of 150 million kilometers, 1 astronomical unit. Stephenson 2-18's radius is about 10 astronomical units. If you placed this star at the center of our solar system, here's what would happen to the planets. Mercury orbits at 0.39 AU. It would be deep inside Stephenson 2-18, completely engulfed. Venus, at 0.72 AU, would also be deep inside the star. Earth at 1 AU would be well within the star's envelope. Mars, at 1.52 AU, would be inside as well. The asteroid belt, stretching from about 2 to 3.5 AU, would be completely engulfed. Jupiter, the largest planet, orbits at 5.2 AU. It too would be inside Stephenson 2-18. Saturn, the beautiful ringed world at 9.5 AU, would sit right at or just inside the star's surface. Only Uranus at 19 AU and Neptune at 30 AU would orbit outside this monstrous star. Think about that. This single star would fill the space occupied by 6 of our 8 planets and all the minor bodies in between. Everything from the Sun's position out to Saturn, a distance that light takes about 80 minutes to travel, would be filled with the tenuous, glowing gas of Stephenson 2-18's envelope. The star's luminosity is equally impressive. Stephenson 2-18 shines with the light of approximately 500,000 to 600,000 suns. Every second, it radiates as much energy as the Sun radiates in more than a week. This enormous energy output, combined with the star's cool surface temperature of about 3,200 to 3,500 Kelvin, necessitates its gigantic size. Despite this immense volume, Stephenson 2-18's mass is estimated at only about 15 to 20 times the Sun's mass. This might seem contradictory. How can something so large have relatively modest mass? The answer lies in density. Density is mass divided by volume. Stephenson 2-18's volume is roughly 8 billion times the Sun's, but its mass is only 15 to 20 times the Sun's. Its average density is therefore about 400 million times less than the Sun's average density. To make this concrete, the Sun's average density is about 1.4 grams per cubic centimeter, slightly denser than water. Stephenson 2-18's average density is roughly 0.000000003. 5 grams per cubic centimeter, far lower than Earth's best laboratory vacuums. The star's outer envelope is essentially empty space by terrestrial standards, yet it's still part of the star, held together by the distant but powerful gravity of the dense core. Light takes about 2.3 seconds to travel from the Sun's center to its surface. For Stephenson 2 to 18, light takes about 83 minutes to make the same journey longer than it takes sunlight to reach Earth. A photon generated in Stephenson 2 to 18's core spends nearly an hour and a half bouncing through the star's interior before finally escaping into space. The star's surface gravity is incredibly weak. Gravity at the photosphere is perhaps 100 times weaker than Earth's surface gravity and far weaker than the Sun's. This weak gravity, combined with the star's intense luminosity, drives powerful stellar winds that blow material off the star's surface at speeds of tens of kilometers per second. Stephenson 2 to 18 is losing mass constantly. Estimates suggest it sheds somewhere between a 10,000th to a 1,000th of a solar mass per year. This might not sound like much, but over just 100,000 years, the star could lose 10% of its mass or more. This mass loss creates a nebula around the star-expelled gas and dust, forming shells and streamers in space. The star is also variable. Like most hypergiants, Stephenson 2 to 18 pulsates, expanding and contracting over periods of months to years. These pulsations change the star's brightness and size. At maximum expansion, the star might be several hundred solar radii larger than at minimum. These pulsations are symptoms of instability. The star is struggling to maintain equilibrium between gravity pulling inward and pressure pushing outward. From Earth, Stephenson 2 to 18 is invisible to the naked eye. Despite its incredible intrinsic brightness, it appears as only a 14th magnitude star, far too faint to see without a telescope. The combination of great distance and interstellar dust absorption dims the star tremendously. Astronomers study Stephenson 2 to 18 using large telescopes equipped with infrared detectors. Infrared light penetrates dust better than visible light, revealing the star's true brightness. Spectroscopy, splitting the star's light into its component colors, reveals the star's temperature, composition, and motion. These observations, combined with models of stellar structure and evolution, allow astronomers to estimate the star's size, mass, and age. Stephenson 2 to 18 isn't alone in the Stephenson 2 cluster. The cluster contains other massive stars, including additional red supergiants that might rival Stephenson 2 to 18's size. However, detailed measurements of these other cluster members are limited, and Stephenson 2 to 18 currently appears to be the largest based on available data. The star won't hold this title forever, not because a larger star will be found, though that's possible, but because Stephenson 2 to 18 itself will change. It's in an unstable, transient phase of evolution. Within perhaps 100,000 years, a cosmic blink of an eye, the star will explode as a supernova, destroying itself and leaving behind either a neutron star or a black hole. Before that happens, it might shrink or expand further, or undergo violent eruptions that temporarily change its size. For now, though, Stephenson 2 to 18 stands as the largest star we've ever found, a monument to stellar extremes, a brief but spectacular phase in the life of a massive star. While Stephenson 2 to 18 currently holds the record, several other stars come close, and past record holders remain impressive in their own right. Scuti, located about 9,500 light-years away in the constellation Scutum, held the title of largest known star for several years. Early estimates placed its radius at around 1,700 solar radii, with some studies claiming over 2,000. More recent observations suggest a smaller radius, likely between 1,200 and 1,500 solar radii. This revision doesn't mean Uy shrunk. Rather, improved measurements and analysis changed our understanding of its size. Distance measurements were refined, temperature estimates were updated, and better models were applied. These changes reduced the calculated radius. Even with the revised size, Uy Scuti is enormous. With a radius of 1,400 solar radii, a middle estimate, it would extend past Jupiter's orbit if placed at the Sun's position. Its volume would contain about 2.7 billion suns. It shines with the light of roughly 340,000 suns. Uy Scuti is also highly variable, pulsating with a period of about 740 days. During these pulsations, the star's radius changes by hundreds of solar radii. At maximum expansion, it might reach 1,600 or 1,700 solar radii. At minimum, it might shrink to 1,200 or 1,300. This variability adds uncertainty to size measurements. A single observation captures the star at one moment in its pulsation cycle, not its average size. The star has a thick, dusty circumstellar envelope created by mass loss. This dust absorbs ultraviolet and visible light from the star and re-radiates it as infrared. The envelope makes defining the star's exact boundary difficult. Where does the star end and the envelope begin? Different wavelengths of light probe different layers, leading to different size estimates. Vy Canis Majoris, about 4,900 light-years away in the constellation Canis Major, is another famous giant. It too once held the record for largest star, with early estimates exceeding 2,000 solar radii. Subsequent studies revised this down to about 1,400 to 1,500 solar radii, still huge, but not record-breaking. Vy Canis Majoris is particularly notable for its extreme mass loss and the complex nebula surrounding it. The star is shedding mass at a prodigious rate, perhaps a 10,000th of a solar mass per year or more. Over its lifetime, as a red supergiant, it has ejected several solar masses of material. This ejected material forms an intricate nebula with arcs, knots, and filaments. High-resolution infrared images reveal this structure in stunning detail. The nebula suggests the star has undergone multiple episodes of mass loss, each ejecting material in different directions. The nebula is also rich in dust, tiny grains of minerals that condensed from the gas as it cooled. Vy Canis Majoris is also one of the most luminous stars known, shining with perhaps 300,000 to 450,000 times the Sun's luminosity. This extreme luminosity, combined with pulsations and instabilities, drives the intense mass loss. The star is fighting a losing battle between radiation pressure blowing material away and gravity trying to hold it in. The star likely has only tens of thousands of years left before it explodes as a supernova. When it does, the nebula around it will be swept up by the supernova shockwave, creating a complex supernova remnant. Westerland 1-26. Located in the Westerland 1 superstar cluster about 11,500 light-years away, is another hypergiant contender. Estimates suggest a radius of around 1,500 to 2,000 solar radii, potentially rivaling Stephenson 2-18. However, Uncertainties in distance and interstellar extinction make precise measurements difficult. Westerland 1 is a remarkable cluster containing numerous massive stars, including Wolf-Rayet stars, supergiants, and hypergiants. It's one of the most massive young clusters in the Milky Way. Westerland 1 to 26 stands out even in this collection of stellar extremes as one of the largest members. Betelgeuse, the bright red star in Orion's shoulder, is much closer to Earth, only about 550 light-years away, making it one of the nearest red supergiants. Its radius is estimated at 600 to 900 solar radii, depending on the measurement method and wavelength observed. While significantly smaller than Stephenson 2 to 18 or UY Scuti, Betelgeuse is still enormous. If Betelgeuse replaced the Sun, its surface would extend past Mars's orbit, possibly reaching the asteroid belt. It would fill the sky from Earth with a disk hundreds of times wider than the Sun appears to us, though this is a moot point since Earth would be inside the star. Betelgeuse is famous for being easily visible to the naked eye and for its variability. The star pulsates semi-regularly with multiple overlapping periods, changing in brightness over months to years. In late 2019 and early 2020, Betelgeuse underwent an unusual dimming event, dropping to about 40% of its normal brightness. This sparked speculation that the star might be about to explode as a supernova. Subsequent observations revealed the dimming was likely caused by a dust cloud. The star had ejected a mass of material that condensed into dust grains, temporarily blocking our view of the star's surface. The star has since returned to normal brightness, though it remains variable. Antares, the bright red star in Scorpius, is another nearby red supergiant with a radius of about 700 solar radii, about the same as Betelgeuse. Antares is slightly more distant, at around 550 light-years. Like Betelgeuse, it would engulf Mars if placed at the Sun's position. What makes Antares particularly fascinating is its binary companion. Antares has a hot blue companion star orbiting it, creating a dramatic contrast. The companion, called Antares B, is hidden in the glare of the supergiant primary. When observed with powerful telescopes, the blue companion appears like a tiny sapphire next to a giant ruby. The system illustrates how different stellar types coexist. Antares A, the red supergiant, is cool and enormous. Antares B is hot, compact, and much less luminous overall, despite its higher surface temperature. The two stars orbit each other over hundreds of years, bound by gravity despite their vast differences. Antares also shows significant mass loss. Observations reveal a complex nebula around the star, created by material ejected over thousands of years. This nebula is visible in infrared images, showing shells and arcs of dust and gas. The mass loss rate isn't as extreme as VY Canis Majoris, but over time, Antares has shed considerable material. The star is also variable, though not as dramatically as some hypergiants. Its brightness changes by small amounts over irregular periods, reflecting pulsations and changes in the envelope's structure. These variations are typical for red supergiants, symptoms of the instability inherent in such large, extended stars. Mu Cephei, also called the garnet star for its deep red color, has a radius estimated at 600 to 1,000, 400 solar radii depending on the study. It's about 6,000 light-years away, making precise measurements challenging. At the upper end of size estimates, it would rival some of the largest hypergiants. The star's deep red color is immediately apparent even in small telescopes. William Herschel, the astronomer who discovered Uranus, dubbed it the Garnet Star because of its striking hue. This deep red indicates a very cool surface temperature, probably around 3,200 to 3,500 Kelvin, similar to other red supergiants. Mu Cephei is also highly variable, classified as a semi-regular variable. Its brightness changes by more than a full magnitude over periods ranging from hundreds to over 1,000 days. These variations reflect the star's pulsations, the envelope expanding and contracting in response to instabilities in energy transport and opacity. The large uncertainty in Mu Cephei's size reflects the challenges of measuring distant, variable stars. Different studies using different methods and observing at different phases of pulsation yield different results. The star might genuinely vary in size by hundreds of solar radii as it pulsates, adding to the measurement challenge. KY Cygni, located in the constellation Cygnus about 5,000 light-years away, is another extreme red supergiant with an estimated radius around 1,400 to 1,500 solar radii. This makes it comparable to VY Canis Majoris and UY Scuti in size. KY Cygni is exceptionally luminous, shining with perhaps 300,000 to 600,000 times the Sun's luminosity. This makes it one of the most intrinsically bright stars known. The high luminosity combined with cool temperature necessitates the enormous size. The star is embedded in a dusty nebula created by mass loss. Infrared observations reveal this circumstellar material, showing that KY Cygni, like other hypergiants, is shedding its outer layers through powerful stellar winds. The mass loss rate is estimated at several 10,000ths of a solar mass per year, substantial even for a hypergiant. RW Cephei, in the constellation Cepheus, approximately 14,000 light-years away, is another hypergiant, with an estimated radius exceeding 1,000 solar radii. Some estimates place it as high as 1,500 to 1,600 solar radii, making it one of the largest stars known. RW Cephei is notable for its extreme variability. It's classified as a semi-regular variable with multiple pulsation periods. The star's brightness changes by several magnitudes over timescales, ranging from months to years. These dramatic variations reflect complex pulsations and possibly eruptions characteristic of stars in the unstable hypergiant phase. The star's spectrum shows strong molecular absorption bands, titanium oxide, water vapor, and other molecules confirming its cool temperature. The presence of these molecules indicates temperatures below 4,000 Kelvin, cool enough for complex molecules to survive in the star's atmosphere. Scorpii in Scorpius, about 8,000 light-years away, rounds out this list of extreme giants. Its radius is estimated at around 1,400 to 1,600 solar radii, placing it among the largest known stars. Scorpii is another semi-regular variable, pulsating with periods of several hundred days. The pulsations cause the star to change in brightness by over a magnitude, easily detectable with modest telescopes. Observations over decades show that the pulsation periods aren't perfectly regular, they vary, reflecting the chaotic dynamics of the star's envelope. The star is also losing mass, though detailed observations of its circumstellar environment are limited compared to better studied objects like VY Canis Majoris. What's clear is that Scorpii, like all hypergiants, is in a transient, unstable phase racing toward its inevitable supernova explosion. All these runner-up giants, UI Scuti, VY Canis Majoris, Betelgeuse, Antares, Mu Cephei, KY Cygni, RW Cephei, AH Scorpii, share common characteristics. They're all cool, red, evolved massive stars. They're all variable, pulsating over months to years. They're all losing mass through stellar winds. And they're all in the final stages of life, with perhaps tens of thousands to a few 100,000 years remaining before core collapse. The exact ranking among these stars remains uncertain due to measurement challenges. Published radii have error bars often exceeding 20%. A star measured at 1,400 solar radii might actually be anywhere from 1,100 to 1,700. This uncertainty means the rankings could shift as observations improve. What's certain is that these stars represent the upper limit of stellar size. They cluster in a narrow range, roughly 1,000 to 2,500 solar radii, suggesting we're observing stars near a physical maximum. Stephenson 2 to 18 sits at the top of this range, currently holding the record, but others approach it closely. These runner-up giants illustrate that extreme size isn't unique to Stephenson 2 to 18. Numerous stars approach or exceed 1,000 times the Sun's radius. The exact ranking depends on uncertain measurements, and the title of largest might change as observations improve. What these stars share is their evolutionary state. They're all evolved, massive stars in the red supergiant or hypergiant phase, nearing the end of their lives. Understanding why requires examining how stars evolve and what drives them to swell to such enormous sizes. Stars aren't born as giants. They start small and grow larger as they age, at least massive stars do. To understand why Stephenson 2 to 18 is so enormous, we must follow the life story of a massive star from birth to its final days. Stars form from vast clouds of gas and dust in space, called molecular clouds. These clouds are cold, dense regions where gravity can overcome the gas pressure. When a cloud or a dense region within it becomes unstable, gravity causes it to collapse. As the cloud collapses, it fragments into smaller clumps, each destined to become a star. The collapsing gas heats up as gravitational potential energy converts to thermal energy. Eventually, the center of the collapsing cloud becomes hot enough, about 10 million degrees Kelvin, for nuclear fusion to begin. Hydrogen nuclei fuse to form helium, releasing enormous energy. This energy creates outward pressure that balances gravity's inward pull, and the star stabilizes. The star has reached the main sequence, a phase of stable hydrogen burning that lasts for millions to billions of years depending on the star's mass. Massive stars, those born with 10 to 50 times the Sun's mass, live much shorter lives than smaller stars. The Sun will spend about 10 billion years on the main sequence, slowly converting hydrogen to helium in its core. A 20 solar mass star burns hydrogen far more rapidly, exhausting its core hydrogen in only about 10 million years, 1,000 times faster. Why do massive stars burn through their fuel so quickly? Massive stars have much higher core temperatures and pressures than smaller stars. At these higher temperatures, hydrogen fusion proceeds at an enormously accelerated rate. The fusion rate increases roughly with the fourth power of temperature, double the temperature, and fusion runs 16 times faster. This allows massive stars to generate the tremendous luminosities needed to support their greater mass, but it also means they consume their fuel rapidly. During the main sequence, A 20 solar mass star is hot and blue, with a surface temperature around 25,000 to 30,000 Kelvin. Its radius is perhaps 8 to 10 times the Sun's large, but nowhere near hypergiant size. It shines with the light of perhaps 50,000 suns. After about 10 million years, the core runs out of hydrogen. Fusion ceases in the core, and it begins to contract under its own weight. This contraction releases gravitational energy, heating the core and the layers around it. Hydrogen fusion ignites in a shell surrounding the now helium core. The energy from shell hydrogen burning heats the star's outer envelope, causing it to expand dramatically. The star begins its transformation into a supergiant. As the envelope expands, its surface area increases enormously. The same amount of energy is now spread over a much larger surface, so the surface temperature drops. The star moves from blue to yellow to red as it cools. Meanwhile, the contracting helium core continues to heat up. When it reaches about 100 million degrees, helium fusion ignites. 3 helium nuclei fuse to form carbon in a process called the triple alpha process. This creates a new energy source, and the star temporarily stabilizes as a helium-burning supergiant. Helium fusion is less efficient than hydrogen fusion and lasts a much shorter time, perhaps 1 million years for a 20 solar mass star, compared to 10 million years of hydrogen burning. The star has become a red supergiant during this phase, with a radius of several hundred solar radii, but it hasn't yet reached its maximum size. After the core exhausts helium, it contracts again, heating until carbon fusion begins at around 600 million degrees. Carbon fusion lasts only about 10,000 years. The pattern continues. Each successive fusion stage burns a heavier element, generates less energy per kilogram of fuel, and lasts a shorter time. After carbon burning comes neon burning, then oxygen burning, then silicon burning. Silicon burning is the last stage because it produces iron. Iron is the most stable nucleus. Fusing iron requires energy input rather than releasing it. Once the core consists primarily of iron, no further fusion can occur. The star has reached the end of the line. Throughout these late fusion stages, the star's envelope swells to its maximum size, becoming a red hypergiant. Why does this happen? Several factors contribute. First, the core burning stages release enormous energy. This energy must escape through the star. The envelope expands to accommodate this energy flow. A larger envelope provides more surface area to radiate away the energy. Think of it like opening a window to let heat escape a room. A bigger window, more surface area, lets more energy out. Second, the envelope becomes convective. Hot gas rises from deeper layers, cools, and sinks back down in giant circulation cells like boiling water on a stove, but on a stellar scale. Convection is less efficient at transporting energy than radiation in some conditions, requiring the envelope to puff up to move the energy outward effectively. The convective cells in a hypergiant's envelope are enormous. Each cell might be larger than Earth's entire orbit. Imagine currents of glowing gas, each carrying the mass of Jupiter, rising and falling over years or decades. These convection cells create turbulence, drive stellar winds, and contribute to the star's variability. Third, the outer envelope becomes very cool, only 3,000 to 4,000 Kelvin at the surface. At these temperatures, the gas is partially ionized and partially neutral. This creates high opacity. The gas becomes very opaque to radiation. like a thick fog blocking sunlight. High opacity impedes energy flow, forcing the envelope to expand until it's thin enough that energy can escape. The opacity in cool stellar envelopes comes from several sources. Negative hydrogen ions, hydrogen atoms with an extra electron, absorb radiation very efficiently. Molecules like titanium, oxide, water, and carbon monoxide also absorb specific wavelengths. Dust grains that condense in the coolest outer layers scatter and absorb light. All these opacity sources work together to trap radiation, forcing the envelope to expand. Fourth, mass loss plays a role. As the star swells and its surface gravity weakens, radiation pressure can drive powerful stellar winds. These winds blow off the outer layers at speeds of tens of kilometers per second. The mass loss might actually allow the remaining envelope to expand even more, since there's less weight pressing down from above. The mechanism driving mass loss in red supergiants and hypergiants is complex. Radiation pressure alone isn't enough. The star's luminosity, while high, isn't quite sufficient to overcome gravity and blow away the envelope directly. Instead, dust formation seems crucial. In the cool outer atmosphere, tiny grains of silicates and carbon compounds condense, like frost forming on a cold surface. These dust grains absorb radiation from the star much more efficiently than gas atoms. The absorbed radiation imparts momentum to the dust, accelerating it outward. The dust drags gas along with it through collisions, creating a stellar wind. Pulsations amplify this process. When the star pulsates, the envelope expands and cools during each cycle. Cooler gas allows more dust to form. The dust is pushed outward by radiation pressure. As the star contracts again, more gas flows outward to replace what was lost, and the cycle repeats. Over thousands of pulsation cycles, the star sheds significant mass. Fifth, the star's internal structure becomes highly complex during late stages. Instead of a simple core envelope structure, the star develops an onion-like layering. The very center is an iron core. Surrounding it is a silicon-burning shell. Outside that, an oxygen-burning shell, then neon, carbon, helium, and finally hydrogen. Each shell burns its fuel at different rates and generates different amounts of energy. This multi-shell structure is inherently unstable. The shells don't burn steadily, they flicker and flash. Sometimes a shell suddenly increases its burning rate, releasing extra energy that propagates outward. This can trigger pulsations or even drive brief eruptions. The envelope must constantly adjust to these fluctuations, contributing to its expansion and variability. The combination of these factors creates the hypergiant phase, a star with an enormous, tenuous envelope supported by energy generated in a tiny, incredibly dense core. The envelope is so extended that its outer layers are barely bound by gravity. The escape velocity at the surface is only tens of kilometers per second compared to hundreds for the Sunday. This makes it easy for material to escape through stellar winds. This phase is extraordinarily brief. From carbon burning onward, the star has perhaps 20,000 years left. Silicon burning, the final stage before iron core collapse, lasts only a few days to a week. The star races through these stages because each fusion process generates less energy and runs faster than the previous one. During this time, the star might pulsate with multiple periods, reflecting different oscillation modes in the envelope. It might undergo eruptions, suddenly ejecting large amounts of mass in brief outbursts. It might vary in size by hundreds of solar radii over months or years. The star is fundamentally unstable, fighting a losing battle to maintain equilibrium. Observations of hypergiants show this instability clearly. VY Canis Majoris has ejected multiple shells of material visible in its surrounding nebula, suggesting episodic mass loss events. Betelgeuse's 2020 dimming might have been caused by a massive dust cloud formed after an eruption. These events show that hypergiants don't simply sit at constant size and luminosity, they're dynamic, changing objects. The star's appearance during this phase would be extraordinary if we could see it up close. The surface wouldn't be smooth and uniform like the Sun's appears. Instead, it would be mottled with enormous convection cells, bright, rising plumes of hot gas, and darker, cooler regions where gas sinks. The cells would change and evolve over weeks or months. Vast prominences, arcs of glowing gas, lifted by magnetic fields, might extend above the surface for distances comparable to the Sun-Earth distance. Stellar winds would blow outward in all directions, potentially not uniformly. Some regions might have stronger winds than others, creating asymmetries in the mass loss. The star's spectrum would show strong emission and absorption lines from the various atoms and molecules in the atmosphere. The lines would be broadened by turbulence, the chaotic motions of gas in the convective envelope. Some lines might show evidence of outflows gas moving away from the star at high velocities. All these characteristics tell us that hypergiants are not serene, stable objects. They're turbulent, violent, chaotic stars pushed to the very edge of what physics permits, barely holding together, racing toward inevitable collapse. Finally, when the iron core reaches about 1.4 solar masses, it can no longer support itself. Electron degeneracy pressure, the resistance of electrons to being compressed, fails. The core collapses catastrophically in less than a second, shrinking from about 5,000 kilometers in diameter to roughly 20 kilometers, the size of a city. The collapse releases an enormous amount of gravitational energy, about 100 times more energy than the Sun will radiate in its entire 10 billion year lifetime, released in less than a second. Most of this energy escapes as neutrinos, but a small fraction drives a shock wave that propagates outward through the star. The shock wave reaches the surface hours to days later, depending on the star's size. For a hypergiant, it might take days for the shock to traverse the enormous envelope. When it does, the star explodes as a supernova, blasting the envelope into space at thousands of kilometers per second. The hypergiant is destroyed. All that remains is the collapsed core, a neutron star, or, if the core is massive enough, a black hole. The envelope, enriched with carbon, oxygen, and heavier elements synthesized during the star's life, disperses into space, eventually becoming part of new molecular clouds, where future stars and planets will form. This is the life cycle that produces hypergiants. Only stars massive enough to go through all these fusion stages, roughly 8 to 30 solar masses, initially become red supergiants or hypergiants. More massive stars might lose their envelopes earlier, becoming different types of objects. Less massive stars never reach the advanced fusion stages and don't swell as large. The hypergiant phase represents the final, desperate attempt of a massive star to radiate its energy before its core collapses. It's a brief, glorious, and doomed stage, the stellar equivalent of a supernova's flash, stretched over tens of thousands of years instead of weeks. Given that hypergiants reach incredible sizes 2,000 times the Sun's radius, and counting, a natural question arises: why don't stars grow even larger? What prevents a star from swelling to 5,000 or 10,000 solar radii? The answer involves several physical limits that constrain stellar size. These limits arise from the basic physics governing stars: gravity, pressure, energy, transport, and radiation. First, there's the relationship between luminosity, temperature, and size. A star must radiate away the energy generated in its core. The rate at which it radiates depends on surface temperature and surface area. Cooler stars must be larger to radiate the same amount of energy as hotter stars. For hypergiants, this works in favor of large size. Their cool temperatures, 3,000 to 4,000 Kelvin, require enormous surface areas to radiate hundreds of thousands of solar luminosities. But there's a limit. If the star cooled below about 2,500 Kelvin, the envelope would become so opaque and unstable that it might not be able to hold together. At very low temperatures, molecules form in the star's atmosphere: water, carbon monoxide, titanium oxide, and others. These molecules increase opacity dramatically. High opacity traps radiation, creating a steeper temperature gradient in the envelope. This can drive convection and instabilities that might disrupt the star. Second, there's the binding energy of the envelope. The envelope is held to the star by gravity. The gravitational binding energy, the energy needed to completely remove the envelope, decreases as the envelope expands. Eventually, if the envelope grows too large, it becomes so weakly bound that even modest energy inputs could blow it away. Radiation pressure from the star's luminosity pushes outward on the envelope. For the most luminous stars, this radiation pressure approaches the force of gravity. If radiation pressure exceeds gravity, the envelope is driven away. This sets the Eddington limit, a maximum luminosity for a given mass, beyond which radiation pressure blows the star apart. Most hypergiants are near but not exceeding this limit. If they were more luminous, they would lose their envelopes rapidly. In fact, many hypergiants do lose significant mass through powerful stellar winds driven by radiation pressure. This mass loss might prevent them from growing even larger. Third, there's the issue of dynamical stability. As envelopes expand, they can become unstable to pulsations. Small perturbations, changes in opacity, energy generation, or convection can grow into large amplitude pulsations. These pulsations can cause the star to expand and contract by hundreds of solar radii. In extreme cases, pulsations might become so violent that they eject material or even disrupt the envelope entirely. Luminous blue variables. Extremely massive, hot, luminous stars undergo violent eruptions where they eject several solar masses in a few years. Red hypergiants might experience similar instabilities, limiting how large they can grow. Fourth, there's evolutionary timescales. Even if physics allowed a star to reach 5,000 solar radii, it might only remain that size for a few hundred years before exploding as a supernova or shedding its envelope. Such a brief phase would be extraordinarily rare. We might expect only one star in the entire galaxy to be in that state at any given time, making detection unlikely. Observational evidence supports these limits. Despite searching our galaxy and nearby galaxies, no confirmed star exceeds about 2,500 solar radii. Most hypergiants cluster around 1,200 to 2,000 solar radii. This clustering suggests we're observing stars near a physical maximum. Theoretical models of stellar evolution also predict maximum radii in this range. When astrophysicists simulate massive stars evolving from birth through their final stages, the models produce red supergiants with radii of 1,000 to 2,500 solar radii, depending on initial mass and assumptions about mass loss and mixing. The models struggle to produce stable stars much larger than this. If the envelope is forced to expand beyond about 3,000 solar radii in simulations, it often becomes unstable, losing mass rapidly or pulsating violently. Another factor is stellar mass. You might think that more massive stars would grow larger, and to some extent, this is true. However, very massive stars above about 40 solar masses often don't become red supergiants at all. They lose their hydrogen envelopes while still hot and blue, becoming Wolf-Rayet stars compact, very hot stars with exposed helium cores. The stars that become the largest hypergiants tend to have initial masses of 15 to 30 solar masses. These are massive enough to evolve through all the fusion stages, but not so massive that they lose their envelopes prematurely. There's also the question of metallicity, the abundance of elements heavier than hydrogen and helium. Stars with higher metallicity have more opacity in their envelopes, which can affect how large they grow. Most hypergiants observed have roughly solar metallicity. Stars with very low metallicity, like the first generation of stars in the early universe, might not have become as large because their lower opacity allowed energy to escape more easily, preventing such extreme envelope expansion. In summary, stellar size is limited by radiation pressure, binding energy, opacity, dynamical instability, and evolutionary timescales. These factors conspire to create a maximum size around 2,000 to 2,500 solar radii. Stars approaching this limit are fighting a losing battle against instability. They're barely holding together, losing mass rapidly, pulsating violently, and racing towards supernova. Stephenson 2 to 18, at roughly 2,150 solar radii, is close to this theoretical maximum. It represents not just the largest star we've found, but likely close to the largest star that physics permits. Numbers like 2,150 solar radii or 10 astronomical units are abstract. To truly grasp Stephenson 2 to 18's scale, we need concrete comparisons that relate to familiar objects and distances. Let's start with Earth. Our planet has a diameter of about 12,742 kilometers. Stephenson 2 to 18's diameter is roughly 3 billion kilometers, about 235,000 times Earth's diameter. If Earth were a marble 1 centimeter across, Stephenson 2 to 18 would be a sphere 2.35 kilometers in diameter, taller than most skyscrapers. In terms of volume, Stephenson 2 to 18 could contain about 13 trillion Earths. 13 million planets, like ours, would fit inside this single star. The number is so large it's difficult to comprehend. Comparing to the Sun is more meaningful since we're measuring Stephenson 218 inches solar units. The Sun's diameter is about 1.4 million kilometers. Stephenson 2 to 18 is 2,150 times wider, giving it a diameter of roughly 3 billion kilometers. If the Sun were a basketball about 24 centimeters across, Stephenson 2 to 18 would be a sphere 516 meters in diameter, taller than most skyscrapers, and wider than several city blocks. If the Sun were a beach ball 1 meter across, Stephenson 2 to 18 would be over 2 kilometers across. In volume, Stephenson 2 to 18 contains about 10 billion suns. Imagine filling the star with suns packed side by side. You'd need 10 billion of them. If you could place one sun every second, it would take 317 years to fill Stephenson 2 to 18. Let's compare to Jupiter, the solar system's largest planet. Jupiter has a diameter of about 140,000 kilometers. Stephenson 2 to 18 is roughly 21,000 times wider than Jupiter. You could fit about 10 billion Jupiters inside Stephenson 2 to 18, about the same number as suns, since Jupiter and the Sun have similar sizes, though vastly different masses. Now consider light travel time. Light, moving at 300,000 kilometers per second, crosses Earth's diameter in about 0.04 seconds. It crosses the Sun's diameter in about 4.6 seconds. To cross Stephenson 2 to 18's diameter takes about 167 minutes, nearly 3 hours. A photon leaving one side of Stephenson 2 to 18 and traveling straight across would take almost 3 hours to reach the other side. For comparison, light takes only about 8 minutes to travel from the Sun to Earth. Stephenson 2 to 18's diameter is larger than the distance from the Sun to Earth. If you could somehow survive inside Stephenson 2 to 18 and look toward the center, you'd see a dim glow from the deeper, hotter layers. The envelope is so tenuous that it's nearly transparent. Looking outward, you'd eventually see stars beyond the envelope. The surface isn't a sharp boundary, but a gradual transition from star to space. Let's consider travel time. The Voyager 1 spacecraft, humanity's fastest and most distant probe, travels at about 17 kilometers per second relative to the Sunday. At this speed, crossing Stephenson 2 to 18's diameter would take about 5.5 years. A trip from the center to the surface would take nearly 3 years. If you could fly an airplane at 900 kilometers per hour through the star's interior, crossing from one side to the other would take about 380 years. You'd need multiple generations to complete the journey. Imagine Stephenson 2 to 18 replacing the Sunday. From Earth's position deep inside the star, what would you experience? First, there'd be no Earth, as it would have been vaporized and incorporated into the star's envelope. But hypothetically, if you could exist there, you'd be surrounded by glowing gas in all directions. The gas at Earth's distance from the star's center would be incredibly tenuous, far thinner than Earth's atmosphere, closer to a laboratory vacuum. The temperature would be around 4,000 to 5,000 Kelvin, hot enough to vaporize any solid matter instantly. The light level would be difficult to predict. On one hand, you're inside a glowing star. On the other hand, the gas is so tenuous it's nearly transparent. You might see a dim reddish glow in all directions, brighter toward the star's core and dimmer toward the surface. From outside Stephenson 2 to 18, at a safe distance, the star would dominate the sky. Suppose you orbited at Neptune's distance 30 AU. Stephenson 2 to 18, with a radius of 10 AU and diameter of 20 AU, would subtend an angle of about 38 degrees, roughly 76 times the Sun's apparent size from Earth. The star would appear as an enormous red disk covering about 12% of the sky. It would cast a dim, ruddy light far less intense per unit area than the Sun because Stephenson 2 to 18's surface is much cooler, but the sheer size would make it visually overwhelming. Despite its incredible size, Stephenson 2 to 18's density is extraordinarily low. Calculating average density by dividing mass by volume gives roughly 0.0000000035 grams per cubic centimeter. For comparison, Earth's atmosphere at sea level has a density of about 0.0012 grams per cubic centimeter, hundreds of thousands of times denser. The star's outer envelope has even lower density, perhaps 100 times less than the average. In the outermost layers, near the photosphere, density might be only 0.0000000003 grams per cubic centimeter. This is a better vacuum than anything achievable in terrestrial laboratories. Yet this tenuous gas is still part of the star, bound by gravity, glowing with the star's light. It's gravitationally connected to the core far below, influenced by convection, pulsations, and magnetic fields. Comparing to other large stars helps put Stephenson 218 inches context. Betelgeuse, at about 750 solar radii, is roughly one-third Stephenson 218's radius. In volume, Betelgeuse is about 420 million solar volumes, 40 times smaller than Stephenson 218. Scuti, at about 1,400 solar radii, is about 65% of Stephenson 218's radius. In volume, Scuti is about 2.7 billion solar volumes, less than one-third Stephenson 218's volume. The difference between Stephenson 218 and smaller giants like Betelgeuse seems modest: 2,150 versus 750 solar radii, only a factor of 3. But because volume scales with the cube of radius, Stephenson 218's volume is 3 cubed, or 27 times larger. It's not just bigger, it's in a different category entirely. These comparisons illustrate that Stephenson 218 isn't just a large star, it's an object operating on a scale that transcends everyday intuition. It's a star whose diameter exceeds the distance from the Sun to Saturn, whose volume contains billions of suns, whose density is lower than the best vacuum humans can create. It's a monument to the extremes that nature can achieve: brief, unstable, and magnificent. Is Stephenson 218 definitively the largest star in the universe, or could larger stars exist, hidden in distant regions we haven't fully explored? This question touches on observational limits, theoretical possibilities, and the sheer vastness of the cosmos. First, consider observational challenges. The Milky Way galaxy contains 200 to 400 billion stars spread across a disk roughly 100,000 light-years in diameter. Despite centuries of astronomical observation, we've characterized only a tiny fraction of these stars in detail. Many regions of the galaxy are obscured by interstellar dust. The galactic plane, where most massive stars reside, is particularly dusty. Dust absorbs visible light, making stars invisible to optical telescopes. Infrared observations can penetrate dust better, but even infrared has limits. Stephenson 2 cluster, home to Stephenson 218, is heavily obscured. It was only identified and studied in detail in recent decades. Other clusters might remain undiscovered, potentially harboring hypergiants as large as or larger than Stephenson 218. Distance also limits observations. Hypergiants are intrinsically very luminous, but beyond about 30,000 light-years, they become faint enough that detailed spectroscopy is challenging. Most known hypergiants are within 20,000 light-years. Hypergiants farther away might exist, but remain unstudied. The Milky Way's far side, beyond the galactic center, is particularly difficult to observe. The center itself is dense with stars and dust, blocking our view. Hypergiants in those regions might be completely hidden from us. Additionally, hypergiants are rare and short-lived. At any given moment, perhaps only 50 to 100 hypergiants exist in the entire galaxy. With such small numbers, the statistical likelihood of finding one significantly larger than Stephenson 2 to 18 depends on luck and thorough searching. Spectroscopic surveys tend to focus on brighter stars. Faint hypergiants in obscured regions might be catalogued but not spectroscopically analyzed, leaving their nature unknown. All this suggests that undiscovered hypergiants could exist. Perhaps one rivals or exceeds Stephenson 2 18 inches size, but lurks in an obscured, distant region we haven't thoroughly explored. Theoretical limits, however, suggest that stars much larger than Stephenson 2 to 18 are unlikely. As discussed, physical constraints, radiation pressure, binding energy, opacity, dynamical instability prevent stars from growing arbitrarily large. A star significantly larger than 2,500 solar radii would likely be unstable. Its envelope would be so weakly bound that even modest pulsations or radiation pressure could blow it away. Theoretical models struggle to produce stable configurations much larger than observed hypergiants. There's also evolutionary timescales. Even if physics permitted a star to briefly reach 4,000 solar radii, it might remain that size for only a few hundred years before exploding or shedding its envelope. With such brief duration, the probability of observing one is minuscule. Given the Milky Way's population of perhaps 60 hypergiants at any time, if the extreme hypergiant phase lasts only 1,000 years compared to a 100,000-year hypergiant phase, we'd expect to see a super hypergiant only once every few thousand years. We might never observe one. What about other galaxies? The observable universe contains roughly 2 trillion galaxies, totaling perhaps 1 billion trillion stars. Surely, among this vastness, larger stars exist. Possibly, but we can't observe them. We can resolve individual stars only in nearby galaxies, the Large and Small Magellanic Clouds, Andromeda, and a few others within about 10 million light-years. Hypergiants in the Magellanic Clouds have been studied. Some are comparable to Milky Way hypergiants VY Canis Majoris, UY Scuti, Stephenson 2 to 18, but none appear significantly larger. Andromeda is too distant to spectroscopically study most individual stars. While we can detect luminous supergiants, determining precise radii is difficult. No Andromeda star is confirmed to exceed Stephenson 2 to 18's size. Beyond the local group, individual stars are unresolvable except in rare cases like supernovae or extraordinary outbursts. A hypergiant at 100 million light-years is simply too faint to characterize. Thus, while the universe's vastness might harbor larger stars, we cannot detect them with current technology. Could different stellar environments produce larger stars? Most hypergiants form from gas, with roughly solar composition, about 2% heavy elements. Could stars in unusual environments grow larger? Low metallicity stars in the early universe might have behaved differently. With fewer heavy elements, their opacity would be lower, potentially allowing energy to escape more easily and preventing such extreme envelope expansion. Models suggest early, low metallicity massive stars were hotter and smaller, not larger. Conversely, very high metallicity stars might have higher opacity, potentially allowing larger envelopes. However, high metallicity also enhances mass loss through stellar winds, possibly stripping envelopes before they grow as large. Binary star interactions could affect size. If a star accretes mass from a companion, it might evolve differently. However, most known hypergiants don't have close companions. Wide binaries probably don't significantly affect evolution. Some theories propose that stellar mergers, two massive stars colliding and combining, could create exceptionally luminous, large stars. But merged stars might also be unstable, quickly losing mass or exploding. In summary, while we can't rule out larger stars in obscured or distant regions, both observations and theory suggest Stephenson 2-18 is near the maximum stellar size nature permits. Future surveys might find a marginally larger hypergiant, perhaps 2,300 or 2,500 solar radii, but a star twice as large is highly unlikely. Improved infrared surveys, future space telescopes, and thorough mapping of obscured galactic regions will clarify the question. For now, Stephenson 2-18 stands as the largest known star and likely close to the largest possible. What awaits Stephenson 2-18? How will this stellar giant end its life? Understanding hypergiant's fate completes the story, revealing that the largest stars also die in the most spectacular ways. Hypergiants are in the final stages of life, burning heavier elements in their cores. Stephenson 2-18 is likely past helium burning, currently fusing carbon, oxygen, or even heavier elements. This phase is fleeting, perhaps 10,000 to 100,000 years remain before catastrophe. During this time, the star is unstable. It pulsates, expanding and contracting over months to years. Pulsations might change the radius by hundreds of solar radii. These pulsations are symptoms of instability. The star struggles to balance gravity, pressure, and energy flow. Mass loss accelerates. Stellar winds blow material off the surface at tens of kilometers per second, driven by radiation pressure and pulsations. The star sheds a solar mass every 10,000 years or faster. Over its hypergiant phase, it might lose 10 solar masses or more. This mass loss creates a nebula around the star. Ejected gas cools and expands, forming shells and streamers. Dust grains condense from the gas, tiny particles of silicates and carbon compounds. This dust absorbs starlight and re-radiates it as infrared, making the nebula glow. Eventually, the core exhausts all fusible elements. It consists primarily of iron, the end product of silicon burning. Iron cannot fuse to release energy. Fusing iron requires energy input. The core has reached the end of the nuclear burning chain. The iron core grows as silicon burning continues in a shell around it. When the core reaches about 1.4 solar masses, the Chandrasekhar limit, disaster strikes. The core can no longer support itself against gravity. Electron degeneracy pressure, which had been supporting the core, fails. The core collapses catastrophically. In less than a second, it shrinks from roughly the size of Earth to about 20 kilometers across, smaller than most cities. The collapse is one of nature's most violent events. Gravity becomes so strong that protons and electrons combine to form neutrons. The core becomes a neutron star matter compressed to nuclear density, where a sugar cube-sized piece would weigh as much as Mount Everest. The collapse releases a staggering amount of energy, about 100 times more than the Sun will radiate in its entire 10 billion year lifetime, released in 1 second. Most escapes as neutrinos, ghostly particles that interact barely with matter. A small fraction of the energy, about 1%, drives a shock wave that propagates outward through the star. The shock heats and accelerates the overlying layers, blasting them into space. For a hypergiant with a radius of 2,150 solar radii, the shock takes time to traverse the envelope. It might take days or even weeks to reach the surface. When it does, the star brightens dramatically, a supernova. The supernova outshines entire galaxies. At its peak, Stephenson 2-18 supernova might reach an absolute magnitude of -17 or -18, comparable to 100 billion suns. If it were as close as Betelgeuse, 550 light-years, it would shine with an apparent magnitude of -8, brighter than Venus, visible during the day. From Stephenson 2-18's actual distance of 19,000 light-years, the supernova would be much dimmer, perhaps magnitude +5 to +8, easily visible to the naked eye but not spectacular. It would appear as a moderately bright new star in scutum, visible for weeks or months before fading. The supernova ejects the entire envelope, 10 to 15 solar masses of material, at thousands of kilometers per second. This material, enriched with carbon, oxygen, neon, magnesium, silicon, and iron from nuclear burning, disperses into space. Over tens of thousands of years, the ejector expands and cools, forming a supernova remnant. The remnant sweeps up surrounding interstellar gas, creating shocks and glowing filaments. Eventually, the remnant dissipates, mixing into the interstellar medium. This ejected material becomes part of future molecular clouds, where new stars and planets form. The atoms in our bodies, carbon, nitrogen, oxygen, calcium, iron, were created in stars and dispersed by supernovae. We are made of hypergiant ashes. The core remnant depends on its mass. For cores below about 2.5 solar masses, a neutron star forms a city-sized ball of neutrons spinning rapidly, perhaps many times per second. If the neutron star has a strong magnetic field and the rotation axis is misaligned, it might emit beams of radiation, a pulsar. For cores above 2.5 solar masses, even neutron degeneracy pressure fails. The core collapses further, becoming a black hole, a region where gravity is so strong that not even light can escape. Stephenson 2-18, with an estimated current mass of 15 to 20 solar masses, will likely leave a neutron star. The exact outcome depends on how much mass is lost before core collapse and how much falls back onto the core after the supernova. When will this happen? We don't know precisely. Stellar evolution models suggest Stephenson 2-18 has perhaps 10,000 to 100,000 years left, possibly less. It could explode tomorrow or 100,000 years from now. On cosmic timescales, both are essentially now. Betelgeuse, closer and better studied, is also expected to explode soon, meaning within the next 100,000 years. When Betelgeuse explodes, it will be a spectacular event, visible during the day, rivaling the full moon in brightness. Astronomers eagerly await it. Stephenson 2-18's supernova will be less dramatic from Earth due to greater distance, but it will still be a significant astronomical event, a supernova in our galaxy, visible to the naked eye, marking the death of the largest known star. After the supernova, the nebula around Stephenson 2-18 will be swept up by the blast wave, creating a complex, beautiful remnant. The neutron star, or black hole, will remain, perhaps orbiting within the Stephenson 2 cluster until the cluster dissolves over millions of years. The hypergiant phase is the final, fleeting act in the life of a massive star, a brief swelling before inevitable collapse and explosion. Stephenson 2-18 and its kin are living on borrowed time, brilliant but doomed, racing toward their spectacular end. We've journeyed through the realm of the largest stars in the universe, exploring Stephenson 2-18, a red hypergiant so enormous that its surface would stretch past Saturn if placed in our solar system, containing the volume of 10 billion suns, shining with the light of 500,000 suns. We've learned why stars become so large, massive stars in the final stages of life, burning heavier elements, swelling their envelopes to maximum size as they race towards supernova. We've seen the physical limits preventing even larger stars: radiation pressure, binding energy, opacity, and instability conspiring to create a maximum size around 2,000 to 2,500 solar radii. We've marveled at the comparison stars whose diameters exceed the Sun-Saturn distance, whose densities are lower than the best vacuum, whose light takes 83 minutes to travel from core to surface. We've examined the runner-up giants, UY Scuti, VY Canis Majoris, Betelgeuse, each enormous, each nearing the end of life, each destined for supernova. We've asked whether larger stars exist and concluded that while possible, Stephenson 2-18 is likely near the absolute maximum nature permits. And we've confronted their fate: core collapse, supernova explosion, enriching the galaxy with heavy elements, leaving behind neutron stars or black holes. These stellar giants remind us of nature's extremes. They show us that the universe contains objects operating on scales that dwarf our everyday experience and imagination. Stephenson 2-18 isn't just bigger than the Sun, it's fundamentally different. It's a tenuous envelope of glowing gas, barely held together, burning itself out in a desperate final blaze before dying in violence. Yet, in their brief existence, hypergiants shape the cosmos. Their winds and supernovae disperse heavy elements, carbon, oxygen, iron throughout galaxies. These elements become planets, life, us. We are made of hypergiant ashes, forged in stars, scattered by explosions, assembled into new worlds. As you drift towards sleep, imagine Stephenson 2-18 glowing 19,000 light-years away. It's light that left when humans were hunter-gatherers, finally reaching Earth today. Captured by telescopes, studied by astronomers. Imagine its scale: a star so large that light takes 83 minutes to travel from heart to surface. A volume swallowing Saturn's orbit. A density almost too low to conceive. Imagine standing at Neptune's distance, gazing at this monster, a red disk covering 12% of the sky, glowing dimly, dominating your view, a dying giant in its final days. Imagine its fate. Perhaps 100,000 years from now, the core will collapse. A shockwave will tear through that vast envelope, and Stephenson 2-18 will explode, briefly outshining 100 billion stars, scattering its substance across light years, seeding future star systems. The largest stars teach humility. Despite our intelligence and technology, we are infinitesimally small, living on a tiny world orbiting a modest star in a galaxy containing objects of such scale we struggle to visualize them. Yet they also inspire wonder. That we can comprehend these giants, measure their sizes, understand their physics, predict their fates is remarkable. We may be small, but we can grasp the immense. Rest well, fellow traveler. The universe is vast, filled with wonders and extremes. Tomorrow, The sun will rise, steady and reliable, a small but friendly star nurturing life on our small world. And somewhere far away, Stephenson 2 to 18 shines, the largest star we know, a monument to stellar extremes, living its final days before its spectacular end. Sweet dreams, knowing that among the stars are giants beyond imagination, brief and brilliant, shaping the cosmos with their lives and deaths, reminding us of nature's power and majesty.